Hi folks, this is your introduction to differentiation 1. Just make sure you have your blank notes in front of you, as later on we'll do some of the first examples in it. Just to begin, I want to introduce this idea of limits, which is a really important concept in differentiation. So consider the expression, the limit as x tends towards 2, so it's x at v arrow towards 2, of x squared minus 4 all over x minus 2. Okay, so I want to see what happens as x gets closer and closer and closer to 2, what happens to the value of this expression. So one thing we could do, or one thing we could consider, is what happens if we actually make x equal to 2. So I'll do this over here. If I make x equal to 2, well, what we get is, if I just substitute my 2 in, I get 2 squared minus 4 over 2 minus 2. So I get 2 squared, which is 4, take away 4, which is 0, and on the bottom I get 0 as well. Now this is undefined, so dividing by 0 is undefined. So this hasn't really given me a usable result here. That's just telling me that when x is 2, the value of this expression is undefined. But remember what the objective here was. I want to know the value of this as it gets closer and closer and closer to 2. So one other thing we could do is we could consider another number that's close to 2 and substitute that in and see if that gets us anywhere. So let's consider a number which is quite close to 2. Let's go for 2.1. So if I substitute 2.1 into this, I end up with 2.1 squared minus 4 over 2.1 minus 2. And if I calculate that out, that gives me 4.1. So you can check that in your calculator, but 4.1 in that case. Okay, so that's a number quite close to 2, got me 4.1. So let's try and get a wee bit closer to 2 then. Let's go for x equals 2.01 instead. So quite a bit closer to 2 now. And let's see what happens to the expression in this case. So in this case I get 2.01 squared minus 4 all over 2.01 minus 2. And then when I calculate that, that comes out to be 4.01. So you can maybe see what's going on here, what's happening as I approach 2, as I get closer and closer to 2. And then let's just take one more. Let's take another number closer to 2. So let's go for 2.001. And let's see what happens to that expression. So 2.001 squared minus 4 over 2.001 minus 2. And when I do that, I get 4.001. And what you'll see if you continue to do that, you'll get closer and closer and closer to 4. If I was to do this for numbers underneath 2, so like 3.99 and 3.999 and so on, the same thing would happen the other side, so they would start getting closer and closer and closer to 4 from the other direction. But what we see in this case is that the limit, I'll do this in red up here, so the limit as x tends towards 2, so it gets closer to 2, approaches 4. Okay. Now there was another way we could have done this. We could have done this a more algebraic way instead of just substituting in values. Now if you consider this x squared minus 4 over x minus 2, so it's x tends towards 2. What I could do with that numerator is I can actually factorise that. So I get x minus 2, x plus 2, as that's just a difference of 2 squares. And that's all over x minus 2. Now what I can do is I can realise that x minus 2 at the top, x minus 2 in the bottom, they can cancel each other out. And that leaves me with an equivalent statement saying that that's just the same as the limit as x tends towards 2 of just x plus 2. Which is a much easier expression, and you'll notice now that if I input 2 into this, I get a nice value of 4. So that comes out to be 4. Just bear in mind though that the original expression was still undefined for x equals 2, but our algebraic manipulation has just made this a bit easier for us to see. In this case, we could just substitute in the value and we get an answer of 4. I'm going to look at one other example. So let's take the case where the limit as x tends towards 5 in this case of 2x squared plus 5. So again, another limit statement. We want to know what happens to this expression as it approaches 5, so it gets closer and closer to 5. Now, because there's no fraction here, I know I'm not going to end up with anything that's undefined if I input a certain value. So this expression 2x squared plus 5 exists for all values of x, which means it's defined for x equals 5 as well. So in this case, all I need to do is substitute in 5 for my x here. So I end up 2 times 5 squared plus 5, which gives me 55. Simple as that. So that's now a lot easier when we don't have anything that's going to come out to be undefined. So like I say, a really important concept for differentiation, as this will be the next part that we'll be looking at, a new definition for the derivative. So the next part is actually starting some differentiation by first principles now. This won't generally be assessed in your exam, but it's a really important thing for you to get your head around in the first place, this idea of where differentiation comes from. So far, if you were asked to differentiate a polynomial, such as x squared plus 2x plus 1, to differentiate that, that's f of x. If I was to work at f dash of x, I would just use my rule here, so I would bring the power down and subtract 1 from the power, so 2x plus 2. Now we are going to look a bit deeper at that now, about what differentiation is actually telling us about the function. I've got a nice function here, and what I'm interested in here is what is the derivative at this value for x. Now just bear in mind what I'm asking here is, when I'm asking for the value of the derivative at that x value, what I'm asking is, what is the gradient of the tangent line at that point? So if I was to draw a tangent line in that just glances on that point and off again, I want to know what the gradient of that line is at that point. Maybe a wee bit like that. Okay, so that's really what we're asking when we're doing a bit of differentiation. Now, if you remember way back to National 5, to differentiate,